Well, first of all, I'd like to thank very much the organizer for giving me the opportunity to present this work, and also to organizing such a conference in such a strange time. So what I'm going to be talking about today is all optical magnetization manipulation. So we will see how we can manipulate, meaning reverse the magnetization, using light and using light only. There at no point we will use magnetic field to reverse magnetization. So this field is interesting since it combines various fields such as magnetism and electronic that gave rise to spintronic, but also ultra-fast optic. And so at the end, we may think about using all of this to build ultra-fast spintronic. It's very interesting in terms of fundamental science, because we are dealing here with very short timescales. Indeed, we will send light to a materials, and the pulse duration of the laser is going to be a few femtoseconds, typically 30 femtoseconds. And at these timescales, the system is totally out of equilibrium. And we usually define temperatures of different baths, the electron baths, because the electrons are going to receive the energy first, a bath for spin and lattice. And you see on this diagram here that if we define a temperature for all those baths, equilibrium appears only after 3 picoseconds. So at a time much longer than the time of the pulse duration. So what is interesting is to try to understand how at those timescales we can define and understand energy transfer, angular momentum transfer, but also charge and spin current. And what is nice about using those femtosecond laser is that it can be polarized, circularly polarized, left or right. And so light can carry an angular momentum that may be transmitted to the rest of the material. It's also interesting for application, because indeed, if we look at magnetic recording, right now it is using a magnetic field, but in order to improve the density, the data storage density, new methods need to be used, and Seagate is proposing heat-assisted magnetic recording, where already in the hard disk, a laser is heating up the system. Here it's for heat only, but we would see that using all optical switching, what we would discuss, we could imagine that we would be able to reverse the magnetization with light only and no need for magnetic field, which is, of course, interesting in terms of energy efficiency. Now, the system that we're going to be using, the experimental setup, is this one. We have this pulse laser, which is creating laser pulses of about 30 femtosecond to 3 picosecond. It's shining on a sample, and then we can probe, so we can measure the magnetization, either using camera and a photo MOC, or we can do some probe experiments. And the experiment that really opened this field was indeed an experiment of a thumb probe experiment performed by Jean-Yves Bigot and Eric Borper in Strasbourg, where they have shown that if they could pump a system, a nickel layer here, and probe it and change the delay between the pump and the probe, they could obtain these curves showing the magneto-optic signal, so basically the magnetization as a function of time. And they observed this ultra-fast demagnetization, which was very surprising, and it's still under discussion. But here, it was demagnetization, was no switching, no deterministic switching. So what I'm going to present here is manipulation of magnetization, so deterministic switching, obtained by shining laser on samples. And we will see that there are two types of all optical switching. There is an all optical helicity dependent switching, and an all-optical helicity-independent switching. And we would see that those two phenomena are very different. And then we would see at the end, quickly, how we can use this type of switching, not only to reverse the magnetization, but to manipulate exchange bias. So to change the sign of the exchange bias field. And I remind all of you what it is about. So here we're dealing with a system. In all the system that I'm going to show, it has perpendicular anisotropy. We shine laser pulses on it, and then two types of effect can be observed. All optical helicity-dependent switching means that you will be able to reverse the magnetization, and the direction of the magnetization is defined by the polarity, the chirality of your light. If it's circularly right polarized or left polarized, you will have two different directions. It's nice because you can determine the direction with the chirality of the light, but we will see that it requires many pulses. Maybe we can do it with a few pulses, but still we need many pulses in order to obtain this very nice reversal here. What is also quite interesting is that it has been observed for many different materials, and we believe that it can be observed for almost all magnetic materials. The second time, which is very different, and we will see why, all optical helicity-independent switching. Here, you take your materials, and if you shine once, you reverse in one direction. If you shine a second time, you reverse in the other direction. And what is very interesting is that only one pulse is needed, but we will see that it's still observed for only a very few type of materials. So the outlines of my presentation is going to be as followed, and we will start with this all optical helicity-dependent switching. So it was observed in 2000, reported in 2007, and this is really the group of theorizing in Mangin that opened this field of all optical switching. You see two types of domains differed by two different colors. So one magnetization is up, the other magnetization is down. And by sweeping a laser beam with one helicity or the other, you are able to write information to reverse the magnetization in one direction or the other. And if you have a linear polarized beam, which is a combination of both, then you have multi-domain state. The model that I proposed to explain this reversal was first magnetic circular dichroism, saying that basically this helicity dependence that we see is due to the absorption asymmetry between one direction or the other. In other terms, it means that when light is seeing with one helicity, if light is seeing a magnetization up or down, the absorption is different. So the temperature rise is also going to be different. And since the probability of going to one state or the other depends on the temperature, then you will have an asymmetry in the hopping, and that can explain the full reversal. However, this means that you need multiple shots because you need multiple attempts for the system to finally go to one direction. Another possibility was to use the inverse Faraday effect, which is basically close to an angular momentum transfer from the light to your materials. What has been observed is that the amount of angular momentum given by the light to the materials is quite small compared to the net magnetization of the materials. But we could understand that if your laser is not only bringing angular momentum, but also heat, we could be able to rise the temperature of the materials close to the ordering temperature, and then this inverse Faraday effect of angular momentum transfer would switch the magnetization. So that was basically the two models that were proposed. At the beginning, it was only observed for some ferromagnetic materials, but we demonstrated that it could be observed for a lot, huge very different materials, sorry for that. So you don't need this gadolinium, you can use terbium, dysprosium, holmium, you can do a multi-layer use alloys, you can have crystalline samples, amorphous, you can have synthetic ferromagnet without any rare earth, and you can also have a simple ferromagnetic layer, like cobalt platinum, cobalt palladium, cobalt nickel. And that also would show this switching using multiple pulse or sweeping the laser, as you can see here. And so we try to find out why it was so universal. Can it be observed for any kind of materials with any kind of parameters, thickness, anisotropy, magnetization, exchange? And we found out that what happened is that if you have a materials which basically either has a very low thickness or low magnetization, you have very nice all optical LECT dependent switching. However, if you have a sample that is too thick, or if its magnetization is too high, then you have thermal demagnetization. And we believe that this is not really due to this all optical switching phenomena, but it is rather due to micromagnetic. Because indeed, if you take, for example, a cobalt platinum multilayer, and if you increase the number of repeats, you have a sample that is thicker. If you have a thin sample with a low number of repeats, you have big domains. If you have a sample with a larger amount of thicknesses, larger magnetization, then you have much smaller domains. And there's formula that gives you basically the domain size as a function of the magnetic parameters. And so our criteria that we could prove right was to say, well, if the laser beam diameter is smaller than the domain size expected, then you will have nice all optical switching. However, if the domain size are much smaller than the diameter of the laser, you will see what we call thermal demagnetization, multi-domains created. So that's why if you have a system with a low, roughly product of the magnetization and thickness that is low, then you will see all optical LECT dependent switching. So our conclusion was to say, okay, it can be observed for any materials. It's just, you just need to make it thin enough if it has a high magnetization. Now, how many pulses do we need? And this is how we proved that we needed many pulses. So we created a whole cross where we could measure the voltage and sending some current. And by measuring the whole resistance or the whole voltage, if it's 1, this means magnetization is up, let's say. If it's minus 1, magnetization is down. We clearly could observe that sending a lot of pulses, at the end, you go to one direction or the other direction, depending on the LECT. But what was surprising is that if we zoomed, at the beginning for the first pulses, you see that it seems that the system is demagnetizing and that it's independent on the LECT. And you clearly see that it needs many pulses to switch. We went further on looking at a whole cross where we patterned the materials is only on the center of the whole cross, right here, because we don't want domains wall or to move from one area to another. So we only pattern this at the center, and we obtain rectangles like this, 10 micron by 10 microns. Again, we have shown that if you use a field, a magnetic field, you can switch magnetization from up to down, and you have a certain signal. And if you use light and light only, you can also go from one direction to another, depending on the LECT. And here we recorded a movie, and you can see here the first pulses from 1 to 12. So here we can clearly show that we need only 10 pulses in order to switch almost totally the materials. But we also see that the reversal is not so simple. We see that it involves nucleation, and domain wall propagation. And you see certain area that has been switched, that reverses, some domains that are growing. So it's a little bit more complicated than what we expected. And here you see also the signal for the two helicity, red switching in one direction, green is switching in the other. And you see that also between pulses, the magnetization changes, and there is probably also some domain wall propagation between two laser pulses. So we find out that what is clear is that nucleation may be dependent on the helicity. What is clear is that domain wall propagation depends on the helicity. Here we created in A at the beginning, we created a domain and we shine light on the domain wall, so between the two domains. And you see that if you use one helicity, you go the domain will go one direction. If you use the other helicity, it goes another direction. And again, if we shine the laser not on the domain wall but inside the domain, you can have even larger domain wall motion. So we're still in the process of understanding exactly what's happening during the first process, but domain wall motion, helicity-dependent domain wall motion, certainly plays a big role. We also created a state diagram in order to understand the effect of the pulse duration. So what you see here is a diagram, pulse duration. So we go from 30 femtosecond to 3 picosecond as a function of the fluence. So the fluence is the energy that is given per pulse. So at 10, for 10 millijoule per centimeter square, on this line here, there's the same amount of energy that is given. It's not given with the same pulse duration. What we observe is that if the fluence is too low, then no switching is observed. If the fluence is too high, then you have demagnetization. But you have narrow window here that shows the clear switching of the magnetization. Again, we use many pulses. It's 800 pulses that have been used in order to obtain the state diagram. What is clear is that in the case of all optical helicity-dependent switching, if you have longer pulse duration, you need a little bit more fluence, but you have a larger range of fluence for which switching is observed. It gets really narrow if you have short pulse duration. So with this, we could look at the position at different positions where we do have switching and obtain the fluence needed for different pulse duration, going from 100 femtosecond to 3 picosecond. And using this 3 temperature model, we could even deduce the temperature of the electrons, the spin and the lattice here in green, for those different points where all of those points show the switching. So you see that also if they all show the switching, the temperature of the electrons are very different depending on the pulse duration. For the short pulse duration, the electron temperature goes very high. And we also see that depending on the fluence, then the temperature of the lattice also change a lot. But what seems to be constant in all those points showing switching is that the temperature of the spins goes to a temperature close to the ordering temperature. So it seems that you need to have the spins going to a temperature close to the ordering temperature in order to observe the switching. So our understanding at this point would be to say, okay, there's a lot to do with micromagnetic, but it seems that at some point you need to increase the temperature of your system close to the ordering temperature and transfer angular momentum to the spins. Now, another thing that I'm not going to discuss, but that may interest some of you, is that in the group, we're also able to switch cobalt platinum with a laser, where the laser was shining an optic switch, creating an electron pulse. This electron pulse was only 3 picoseconds, and we could demonstrate the switching of the cobalt platinum with one single electron pulse of 3 picoseconds. So with that, let's go to the other type of switching, which is all optical LECT independent switching. So in that case, it has been reported by many groups now. In that case, you send one pulse, you switch in one direction, send another pulse, goes in the other direction. And most of the systems that have been studied are gadolinium based. So either gadolinium iron cobalt alloys, gadolinium cobalt alloys, gadolinium cobalt multilayers. And so it was demonstrated that as soon as you have some gadolinium, it's likely to show this effect. This conclusion was true 2 years ago, but now it's not true anymore, since single pulse all optical switching has been observed on different materials like magnesium, return, gallium, and terbium cobalt. Now, is it exactly the same type of switching? This needs to be discussed. And so, no, you don't need a gadolinium-based sample to see a single pulse switching. But let's look at the gadolinium iron or gadolinium cobalt system. It's interesting because the switching has been explained by a pure thermal effect where both sublattice demagnetize. And you see that the relaxation time, the speed of this demagnetization is different for iron. It's relaxed quickly, than for gadolinium that relax slowly. And so at some point, you come to a ferromagnetic state. And then because of angle exchange or maybe just angular momentum transfer from one lattice to the other, you have the switching. So you have a toggle switching that is observed for this kind of system. What we studied is different gadolinium iron cobalt. And gadolinium iron cobalt is a ferromagnetic material. And it's quite interesting because it has two sublattices, the gadolinium sublattice and the cobalt sublattice. And those two the magnetization of the two sublattices are cobalt antiparallel. So you can come to a point for certain concentration, the net magnetization of the two sublattices are equal, and the net magnetization is 0. That's what we see here for a concentration close to 25%. So in that case, magnetization decreases and the coercivity diverges. That's what we see here for the different concentration. If you do a state diagram, again, pulse duration as a function of fluence, here you just send one pulse, and you see that the state diagram is totally different for all optical LECT independent switching than for all optical LECT dependent switching. So it's not at all the same mechanism. And in this case, you favor very short pulses. If your pulses are around 30 frames per second, you see you have a large range of fluence where you do see the switching. Whereas if you have low fluence, there's no switching. If you have fluence that is too high, you have multi-dominant state. So this particular shape, we observe this particular shape of the state diagram for all the gadolinium iron cobalt that we have studied. And indeed, you see this triangular shape showing the state diagram, pulse duration as a function of fluence, and this area in the triangle is the area that is switching. And so you see that depending on the concentration, the minimum fluence decreases and changes. You also see that you cannot observe the switching above a certain pulse duration. So that's our critical pulse duration here. And you see also that the slopes for the triangle is different depending on the concentration. And when we try to look at those three parameters for the different concentration, that's what we observe here on the bottom. So you do have a low switching fluence if you are close to compensation. And this is reproduced for layers that are 20 nanometer thick or 10 nanometer thick. This slope here, it changes with the concentration, and the more gadolinium you have, the smaller, the higher the slope is. And again, if you want to have a long pulse duration, critical pulse duration, then you also need to be close to the compensation. And this is more or less in accord with a 2-temperature or 3-temperature model. The state diagram could be reproduced by the 2-temperature model. Indeed, if you have not enough fluence or a pulse duration that is small, then you do see you don't have a switching in the modeling, whereas you see modeling only for a narrow window of fluences. What I will not discuss here, but I really think you should watch this video given by Quentin Remy in the next talks, where he's presenting that he was able to switch cobalt platinum with a single pulse by demagnetizing the gadolinium, and that this switching was ultra fast, probably certainly less than 1 picosecond. So now let me finish very quickly with the possibility of manipulating not only the magnetization, but exchange bias. As you may know, exchange bias appears in system where you have a ferromagnet and an antiferromagnet are coupled. If you are above the near temperature, then the reversal of the magnetization is not affected by the antiferromagnet, and you have an hysteresis loop that is centered around 0. If you go below the blocking temperature, then you have a shifted hysteresis loop because of the coupling between the ferromagnet and the antiferromagnet. And so we played with one antiferromagnet, iridium manganese, and on top of it, we put it either cobalt platinum, and remember, cobalt platinum shows all optical LECD dependent switching, and we put it also gadolinium cobalt that shows all optical LECD independent switching. We could induce some exchange bias in both systems. And what we have shown already a few years ago is that for cobalt platinum, if you send many pulses, or if you sweep the laser on the surface, not only you change you reverse the magnetization, but you can also change the exchange bias. You see here, a negative exchange bias. If you send a lot of sigma minus, you will reverse the exchange bias, and the exchange bias can be reversed back with another LECD. But here, you still need many pulses. And now what we demonstrate very recently, not published yet, is that if you put cobalt gadolinium with only one single pulse, one single femtosecond laser pulse, you can change the sign of the exchange bias. And that's what we see here for a lot of pulses. Each time the exchange bias sign is changing. And this is really, I believe, amazing that the exchange bias can be set with just one femtosecond laser pulses, and you don't need an annealing for 2 hours or something like this. So this is my outlines and my conclusion. I showed you 2 different type of all optical switching. I've tried to show you what we understand and what we do not understand about those 2 different switching. And I also showed you that this femtosecond laser pulses can manipulate magnetization, but also exchange bias. And before finishing, I would like to thank you very much for your attention, and also acknowledge all the people that I had the chance to work with. With that, I would like to thank you very much.